All right, guys, Mr. Antonucci here, and in this video, we're going to talk about section 4, using calculus to graph functions, and our objectives are to graph functions using calculus and obtain information about a function from its derivative. Now, when you're graphing functions using calculus, there's this 7-step process that we're going to follow here. I'm not going to read all through this because we're going to do this as we go through a specific example here. So now we want to graph the polynomial function 3x to the fourth minus 8x cubed. Okay, so the first step is, since this is a polynomial, its domain is going to be all real numbers. And the first thing we want to do is find the intercepts. So if we plug in 0, then the function is going to equal 0, and then that is going to be an intercept for this one. So f of 0 equals 0. All right. Then you find the x-intercept by setting the function equal to 0. So 3x to the fourth minus 8x cubed equals 0. You can factor out an x cubed and get 3x minus 8 equals 0. So x equals 0 or x equals 3/8. So the two x-intercepts are x equals 0 and x equals 8/3. So we can actually plot those points if we put 0 right there and then 8/3, comma 0, which would be right about there. 8/3 is 2 and 2/3. So the second step you want to do is identify any asymptotes. So since this is a polynomial, polynomials have no asymptotes, but the end behavior of f is going to resemble, so I'm going to put approximately equal to y equals 3x to the fourth. So we know that as x approaches positive or negative infinity, the graph's going to behave like 3x to the fourth. So it's going to increase to the right and rise to the left as well. Okay, so now step 3 is to determine the critical numbers. And so we want to do that next by setting the derivative equal to 0. So f double prime, or excuse me, f prime is equal to 12x cubed minus 24x squared. Set that equal to 0. And then as we set that equal to 0, we can go ahead and factor it. So take out a 12x squared, and you'd have x minus 2. Set that equal to 0, and you have x equals 0 or x equals 2. So the critical numbers are 0 and 2. Then we can go ahead and get the function values at those points and plot those. So f of 0, plug 0 into the original function, you would get 0. And then if you plug 2 into the original function, I already figured this out, you get negative 16. So we can plot those points. 0, 0 is already on there, but we know this is going to be a critical number. And then at 2, negative 16, we know that's also going to be a critical number as well. So we can just kind of label those. Then we can get the second derivative. So the second derivative is 36x squared minus 48, which 48x, excuse me. And then we can factor out a 12x and get 3x minus 4. Okay, so we got the critical numbers, plotted those points, found the second derivative as well. Then step 4, we want to use the increasing decreasing function test to identify the intervals on which f is increasing or decreasing. So what we're going to do here is set up some intervals. So the derivative was equal to 0 at x equals 0 and 2. It was never undefined. So we're going to set up some intervals here. So the interval, so negative infinity to 0, 0 to 2, and then 2 to infinity. Then we're going to look at the sign of f prime. So all we do is pick a value on that interval and test it in the derivative. So if I do x equals, let's say, -1 and plug it into f prime, the answer ends up being negative. Okay, so the conclusion is that f is decreasing on that interval. If you go from 0 to 2, plug in a number in the first derivative. Let's say x equals 1. If I plug in 1 to the first derivative, it's negative as well. So f is decreasing on that interval. And then if I plug in another number on the next interval, let's say x equals 3, the derivative is positive on that interval. So f is increasing. So we know the intervals of increase and decrease. Then step 5 is to use the first derivative test based on the table, or the second derivative test to determine any local or relative extremum. Okay, so based on this table, we have a sign change at x equals 2 for the derivative. The derivative changes from positive to negative at x equals 2. X equals 0 was our other critical number, and you see the sign does not change between those intervals that it switched at x equals 0. So this is neither a relative max or a relative min, but x equals 2 is a relative min because the derivative changes from negative to positive at x equals 2. So that's a critical number, and we know that it's going to be a min. And this is going to be a neither. All right. So then step 6 is to use the test for concavity to determine the intervals where the function is concave up or concave down. Now remember, previously we found that f double prime of x is 12x times 3x minus 4. And if we set that equal to 0, we'd have x equals 0 and x equals 4/3. So we can use 0 4/3 to form 0 and 4/3 to form the intervals for our test for concavity. So if we do our interval here, the interval negative infinity to 0, then 0 to 4/3, and then 4/3 to infinity. Okay, this time we're looking at the sign of f double prime because we are concerned about concavity. So if we plug a number in each interval in the second derivative and look at its sign. So the first interval, I'm going to test -1. If I plug in -1, you end up getting a positive value. It doesn't matter what the number is, just if it's positive or negative. So our conclusion is that it's concave up on that interval. From 0 to 4/3, the second derivative is negative, so it's concave down on that interval. And then on 4/3 to infinity, if we plug a number in on that interval, let's say 2, you would get the second derivative is positive, and that's concave up. Now, at x equals 0, we have a point of inflection because the second derivative changed sign. Similarly, at x equals 4/3, you have a point of inflection. We already graphed the point when x equals 0. So we will want to figure out the value of the function at 4/3. So f of 4/3 is equal to negative 256 over 27. Okay, so we can go ahead and plot that on our graph. So 4/3, negative 256 over 27 is almost negative 10. So we'll go 4/3, negative 10, almost negative 10. And that's a point of inflection. And then um, x equals 0 was a critical number, but it's not a relative max or relative min, but we know it's a point of inflection. Okay, so then we're going to graph the function using the information from the table. And it might be helpful to um, find the slope at a couple points or graph a couple additional points as well. So if we plug in -1 to the function, you end up getting 11. So -1, 11 is another point. So we know that the function is decreasing from negative infinity to 0. That's the next significant point. Okay. So we also know that it's concave up on that interval. So the graph's going to go down and look like a cup. Then from 0 to 4/3 is our next interval. The concavity changes because we have a point of inflection, but you don't have a relative max or a relative min. So it switches from concave up to concave down, but still decreasing. Then from 4/3 to 2, the first derivative is still negative, but the concavity changes again to concave up. And then at 2, you have a critical number, which is a local min. The graph changes to increasing, but it's still concave up. And then it rises to the right. And the end behavior on both sides, remember we said, looks like y equals 3/4, excuse me, y equals 3x to the fourth power. All right, so that was how we graph this one. And remember the 7 steps here. If you just follow these steps, you should be good. Now, there's many other functions you could graph using this procedure. You could do rational functions. Um, you could do trigonometric functions. You could do logarithmic functions. You could do functions with rational exponents, all sorts of things. We're just going through polynomials here to just kind of uh, get a get a taste of things. All right. Hope that's helpful to you. Take care.